half cancel. Then you have to divide that by 10 to the minus 6 to put it into terms of dB microvolts. Y'all with me, class? Once you do that, right here, that's where you start. So I think it's 133.9 on dB microvolts. Is that right, class? Just tell me. That stays that way until you hit the first break frequency, which is at 5 point, whatever it was, 6.37 megahertz, is that right? All right, it stays there. Then at this first break frequency, it starts coming down at a rate of minus 20 dB per decade. You all agree? It keeps coming down until I hit the second break frequency, then it's coming down at minus 40 dB per decade, correct? Now we have to locate the frequency we want the value at of the source voltage. That was the 11th harmonic, right? If the actual fundamental is 10 megahertz, the 11th would be 111 megahertz. Y'all follow? So I come way out here to 111 megahertz, or 110 megahertz, pardon me. And that's where I want this value. So now we're going to get that value. Please just make sure you hear and understand everything I said. You know how to get tau? Tau rise is given. Those are the two important frequencies. You start out flat, and you have to get the magnitude. 20 times the log of 2 times A times tau over T. Everybody good on that? And you divide it by 10 to the minus 6. So now to get the value out here of this, right here, way out at 110 megahertz, we start by saying this value of the 11th, I'll just put 11, in dB microvolts of the source, this is going to be the source, is going to be equal to that 133.9. That's the value it starts with. Then minus 20 times the log of the upper frequency, which is 15.92, over the lower frequency, which is 6.37. Then I have to go down and do the 40 times the log of the upper, because now it's dropping at 40 dB per decade. If it was over just one decade, it would be 40 dB. 2 decades, 80 dB. Right? If it's not a decade exactly, then you have to take the ratio of the upper versus the lower frequency. Here, I start right here, where I left off. That's 15.92. That's my lower frequency, so I divide it through. So it's 15.92. My upper frequency is this, 110 megahertz. Now I'm just not going to bother to put the meg down. So that has a value, and I think it was 92, but you check me on that. Anybody confirm or deny? Is it 92 exactly? 92.45? So this is 92.45 dB microvolts, right? That's the source value. Now we have to figure out what it is at the load, so we need the transfer function. Everybody hear me on this? We need the ratio of output to input voltage. I'm calling it the transfer function. The transfer function of this, I want to put it over here, is what? Well, that's a simple voltage divider. This is the output voltage, and this is the source voltage. We want the ratio of output to input. That is called the transfer function of a circuit. Y'all hear me, class? It's always the output over the input, whatever it may be, voltage, current, doesn't matter. So now I come over here, and I say, in general, for a circuit like this, you work in the impedance domain. The impedance of a capacitor is 1 over J omega C, correct? We're at discrete frequencies. Specifically, we care about the frequency of 110 megahertz. Y'all hear me on that? So we evaluate this capacitor of reactance at 110 megahertz. That means it's going to be 1 over J 2 pi times, and then it's going to be 110 times 10 to the 6 times C, which is 70 times 10 to the minus 12. You can tell me what that is. Just tell me the value of that.
Minus 20.7.
Check it out. Minus it's J 20.7, right? Minus J 20.7 ohms, right? Is that right? Okay. So this is minus J 20.7 ohms. Now last time I made a mistake and I put the R over that. This is here are the capacitors, the load. So when we look at this transfer function, H, And I just care about the magnitude, h of 11, I'll just put this right here. And I only care about the magnitude. So I take a look at that. It's this impedance over the sum of this plus this magnitude. I'm just gonna put it down. Magnitude of minus J20.7 over minus J20.7 plus 100 ohms. Y'all follow me? Can you give me the magnitude of that? I think it's 0.29. Could you tell me? 0.202. Y'all get that, guys? Is it 0.2? Yes. Okay. Equals 0.202. Now, we get the value of the output voltage. By doing, what do I do now? Really, I'm just gonna take 20 times the log of that. Y'all follow me? That's all you have to do and add it to that value. All right, because it's the H, it's really H times Vs would be equal to V out. When you do it logarithmically, you'd have 20 times the log of Vs over 10 to the minus 6, which is exactly what we have right there, plus 20 times the log of the transfer function. So now, to get V out in dB microvolts, I take this, 92.45, plus 20 times the log. You don't have to divide this by 10 to the minus 6. The log of that, which is 0.202. And this comes out something like 78 point something dB microvolts. Can you give me it?
78.58.
78.58 dB microvolts. Now that's the worst case, the largest it could be. And actually, if you remember those sync functions, they do this. So it could be a lot less, right? But it's going to have a limit. That's the peak value, and that's what you worry about in EMC. Always the worst case. Y'all follow me on that? Any questions about any aspect of that problem? Yeah?
Can you remember how to find the initial level? The 133.9?
All right. I don't know if you can read my writing, but that's 20, right, times the log, because this is in dB microvolts. That's 2 times A times tau over T over 10 to the minus 6, right? All right, tau over T is the duty cycle. It's 1/2. It's 50%. Yeah.
Will we ever have a situation where we have another quarter frequency?
Another one?
Quarter frequency? Like
Well, this is for a trapezoidal wave. Now, if the waveform, remember, it's not perfect square, it's trapezoidal. It has rise time, on time, fall time. If you had something that had, say, a rise time and then another time that slowed it down, then flattened, then you'd have a different form. Can you let them in, guys? Just keep that door open if you don't mind. Just leave it open. And open that one up in this, I think the vent's blowing, but turn down that temperature just a little. I'm not feeling anything, but I hear something. Just turn it down a little bit. I'm trying to get as much air through here as I can. If somebody is sick, hopefully nobody will get it because it won't be here very long. I mean, we'll blow it out. Thank you. All right. Any other questions? Yeah. Tau rise, that's stated explicitly. That was given. Now, if I drew a waveform, you should be able to figure out the rise time. Right? It's the time that goes from the low state to the high state. That's it. You all know what rise time is, I think, right? You know how to do it. Any other questions about that? What? You're looking at me like, I don't trust you. I'm telling you what you need to know, and why you need to know. I can't be any clearer. Any other questions? I give you a bunch of problems, did a bunch of problems. I don't think I did all the problems that I gave you, but I did quite a few. Any other question about any problem I gave you?
Could you go over 3.2.6?
Yeah, but you're gonna have to refresh my numbers. I was coming in today, and did I see a lot of traffic? Everybody's coming in for the game at the same time. It's an 11 a.m. game, right? So they're going to be in. They're not coming in tomorrow morning. Well, maybe someone. They've already blocked off that lot over at Beardy's Coliseum. That That didn't used to happen until later today, unless they have it all blocked off for RVs already. Okay, what else? Go ahead, you got a couple.
You got a circuit, with a current source,
What is it? Is this the one with the inductor?
Yes.
Didn't we do this one?
Yes, sir.
All right, I'm gonna sketch it, we'll go through it kinda quick, because this is one I know, I remember doing. You have an inductor, or you have a current source here, I, and this is a square wave, and then it comes in as a resistor R, right?
Yes.
And then it's
One
a-
out.
and this is parallel with the inductor, and the L is two, right, two nanometers, and this is 1 ohm, correct? Right?
Yes.
It doesn't matter what the values are, and this is a square wave that he gives you, like, I think it's like this, you tell me if I'm wrong.
It is.
And this value,
5.
and this is 2 seconds, right?
Yes.
1 second? Okay. Well, from that, I know I did this one, but how many remember me doing it?
I just went back my notes and I thought.
Alright, but you know, just to keep everybody on the same page with this one, this is an easy one. You're gonna get something like this on the final exam. Let me say that again. You're going to get a problem like this on the final exam. Okay, now you know. Some people say I wasn't clear about what I'd be covering. Come to class, you'll figure it out. Okay, if we take a look at this, first thing we need to do is what? We need to get the Fourier series, exponential Fourier series for the actual waveform here, the current wave. You all agree with that? All right, how do you do that? Well, I'm just gonna write it out. The current waveform, I of t, because it is periodic, is given as a summation of c of n e to the j n omega naught t from n equals minus infinity to infinity, right? And the value of c of n, we know, is simply what? It's 1 over the period, integral, I always go from like t from minus a quarter to really t times 3/4. 3/4. The reason I do that is because I don't stop or start where there's a transition. I move the window that has to be a total distance of t, so I adjust it so I don't start or stop at a point where there's a transition taking place. And then it would be simply my I of t times e to the minus j n omega naught t dt. Let me cover it point by point that people might not know. How do I get omega naught? What is that? It's 2 pi times the fundamental frequency. The better question is, how do I get the fundamental frequency? Right, and what is t in this one? 2 seconds. Right, so let's start there. T is equal to 2 seconds. Does everybody understand that? Just by observation. It wasn't stated explicitly. Now, after that, when you take a look at this, the fundamental frequency is 1 over t, which is 1/2 hertz, or 1/2 cycles per second. Does everybody follow me on that? When I multiply that by 2 pi, I get pi. That means omega naught is pi radians per second. Clear? Now I've got that. Now the next thing I have to get, well, I'm going to get this value of c of n, but I'm not going to use that integration. That'll work. You can do that if you want. You can just integrate the function right there. It's not a bad one. But what I'm going to do is take a derivative. So when I take the first derivative of this is the thing I really urge you to remember. I get this, and this, and this, and this, and it repeats itself, right? And then over here, the negative. The value here is going to be 5 with a delta t. The value here is minus 5 delta of t minus 1 second. This is 5 delta t, and it's going to be minus 2 seconds and so forth. You all follow me how I got that? Now that delta function series right there, when I take a derivative of this, that means the c of n gets swayed by j n omega naught. So now I have a summation n equals minus infinity to infinity of j n omega naught, I'm leaving it as that for a reason, times c of n, times e to the j n omega naught t, and I can say this itself is a Fourier series, but instead of having this down here, I'll call it c of n prime times e to the j n omega naught t. And that means my c of n prime is equal to 1 over t, the integral minus t over, since the period is 2 divided by 4 is minus 1/2 second to 1 1/2 second of that delta function, 5, and it's delta of t minus delta of t minus 1, and then it's times e to the minus j n omega naught t dt. Is everybody following on this? Only thing I've done is I've stated explicitly what goes in there. Now you evaluate. Well, the delta functions are the reason for this whole business, because integrating a delta function is simply a matter of finding out where it turns on and evaluating the values of the functions next to it at that point. Clear on that, everyone? All right. So what's it going to be for this? C of n double prime or C of n prime? I'll put it up here. Well, it's 1 over t. T is 2. There's 5 in front. So it's 5 halves. That's the weight in front of all this. First delta function turns on at 0. E to the 0 is 1. So it's 1. Now, next delta function turns on at 1 second. Can you all see that, everybody? In the back there, can you all see it back there? 1 second. So I evaluate this at 1 second. It's just e to the minus j omega naught. And there should be an n in there. I'm trying to put it down. N omega naught. So it's e to the minus j n omega naught as such. And that's it. Y'all follow me? Now you have to divide that by j and omega naught to get the value of c of n that we care about. Correct, class? When I look at this, I'll put it up here. That's going to be c of n is equal to 5 over 2 over j and omega naught times this. 1 minus e to the minus j and omega naught. Now I'm going to put the values of omega naught in there, and we'll talk about analyzing it rationally. We're going to look at the odd values and the even values. That's the simplest way to do this. So we take a look at this. I have c of n equal to 5 halves. This is 1 minus e to the minus j n pi. Over, down here, we have j n, and this is going to be pi here. Y'all agree with me? Now I can do something if I want to. I could turn that into a sine function. I could easily turn it into a sinc function. I'm not going to worry about it. The reason is I can see there are obvious zeros, and there are obvious values they're going to have. They're just 1. For any value n odd, this is the point I made last time. How many remember that? When n is odd, what happens? What is e to the minus j pi? Anybody? E to the minus j pi. Same thing as e to the j pi. Plus or minus the same, right? It's what? Minus 1. Minus 1. And then I have 1 minus minus 1 is 2. Y'all follow me? And that will be true for any odd value. This will double. Y'all follow me? It just becomes 2. Now, what about even values? What is e to the j 2 pi? Or e to the minus j 2 pi? 1. 1 minus 1 is? For all the even values, it's 0. Y'all follow me? For all the odd values, the top part becomes 2. So I can say that c of n odd is equal to simply 2, and the 2 downstairs cancels, so I have 5, right? I have 5 over jn pi, or really I can say it's minus j over n pi. That will be the value of c of n, right? Good?
You need to put 5 back in there?
Yeah, times 5. Times 5. My bad. Yes, you have to. The 2's cancel. When this becomes 2 for any odd value, cancels that to the 5 remains, and that's my mistake. All right, I've got that. Now, really, how could this be rendered? This is c of n. You can do it a few ways. It's what? It could be what? Well, it could be minus 5 over n pi, right, at an angle of 90 degrees. That's one way to do it, correct, class? Another way is you can incorporate the minus j, and that's what? That's minus 3/2 pi, isn't it? Follow me on that? Minus j, or whatever you want to call it, but that's it, basically, right? So it would be minus pi over two, or minus j pi over two, or plus j 3/2 pi, my bad on that. But you all follow me, it's just the phase angle. Now, that gives you the value of C of n1, and adding, just looking at this, what is the average value of C0? I'm gonna see it's gonna be the magnitude 5, right, divided by 2.5. You all follow me in that? So it's simply 5/2. 1/2 the value of the peak, because it's 50% due to second. Okay, now, if you want the values of the, really at this point, the problem pretty much is done, because we just turn this into a cosine series, don't we, class? He leaves it as a sine, you can put it as a cosine, it doesn't matter. So now I'm gonna take this thing, and I'm gonna make it the cosine series, phi of t. And that's just C0 plus the summation n equals 1 to infinity, right? Now remember, we could just say n odd here. We don't have to go from 1 to infinity, we can just say n odd, because all the even values of C of n are 0. Do you all follow me in that? I might as well just say this, say n odd. It's going to be the value, the magnitude of C of n, which is just going to be 5 over n pi. Then it's going to be the cosine of n omega naught times t. Well, that's n times pi times t. Then it's going to be plus the phase angle of C of n. Well, the phase angle on that one is what? That's, I can say just minus pi over 2, correct? Because it's minus j. I'm going to leave it like that. That'll work, right? So that is the input signal. Agreed? Now, what else could I do? Couldn't I turn that into a sine? I could just get rid of that 90-degree phase shift and turn it into a sine wave if I want. It's not necessary, but it'll do. I mean, if you want to do it that. He left it as a sine. It's his business. I mean, if he wants to, so be it. But you all follow me on that. Either way, it's exactly the same information. Now I need the transfer function of this to be done. Now I'm going to get the final output form, which is the current. I think here, right? Isn't that the output? So what's the transfer? So I need my transfer function. I'm going to do it over here. So what's that going to be? Remember, this is the source current. He wants the current over here. This is current division, is it not? Anytime you have two parallel elements and you want the current through one of them, you simply take, if I want IL, and I'm going to do this in the frequency domain, n omega naught, that's equal to the actual IS, and this would be I'll just put n omega naught, it's the value, or whatever harmonic you want. Then it's times the opposite impedance, 1 over the sum of the two, right? The sum of those impedances is 1. Matter of fact, let's do it this way. Let's just get the transfer function. And I'll just call that h of n omega naught here. That is going to be what? That's the opposite is 1 over the sum of the two, which is 1 plus j times n times omega naught, which happens to be pi, times the value of L, right? That's the transfer function. Now it has a magnitude and a phase, doesn't it, class? If I looked at that, and I want the magnitude of h of n omega naught, what's that going to be? Anyway, make sure you know how to do this. Magnitude, what do? Top part is just 1. What about down here? Square the values of the real and the imaginary part, take the square root. So this is the square root of 1 plus n pi L squared. And I left it this way for a reason. Correct, class? That's important. Does everybody see it back there? All right, what about the phase? All right, well, the phase of the top is just 1 at an angle 0 degrees. Phase of the bottom is what? It would be the inverse tan of n pi L over 1. When I take that angle on top, it becomes negative, so the phase would be equal to minus the tangent of n pi L over 1. And that would be the actual value of the angle. Now that we will use in the final form. And I'll put the final form, I'm going to erase all this and put it right here. Okay, so now the final form of the answer is very similar to this, except what? C0 gets multiplied by H, evaluated at 0. Do y'all follow me? Well, what is H at 0? What's the DC value? It's just 1, isn't it? N is 0, look at that, it's 1. So I'm gonna say my IL of T is C0 times 1, or just C0, and I'll leave it as C0. C0 is 5 halves. Plus, and now you do what? You go the summation from N equals 1 to infinity, N odd, right? And this is 2 times the magnitude of C of N, which is magnitude of 5 over N pi, which is 5 over N pi, times the magnitude of the transfer function. Magnitude of that transfer function is 1 over square root of 1 plus N pi L squared, right? So now I have that, then I put the cosine term next to it, cosine of N pi T, plus the phase angle, the original phase angle, which was minus 90, correct? Minus 90. And then I have to put minus tan minus 1 of N pi L. And that is that is the answer in the time domain. And if I ask you, this is a typical question I would ask. I would want to know the value of the current of the 5th harmonic. Do y'all hear me? How do you get that? The value of the current in the load at the 5th harmonic. It's this evaluated at n equal 5. That's just magnitude. Y'all follow me on that, class? How many do? All right, what's the angle? Then you would have to evaluate what? Minus 90 minus that angle. Do y'all follow me? If it's a cosine form, and that would be the angle. Do y'all see that, class? Now, if it was in a sine form, it would just be that angle. All right? Clear on that, everyone? And that's it. All right? Yeah.
I remember that there is a 2 to do that, but why do you multiply the magnitudes by
2? Because when you do you turn it into remember the first series was doubly infinite, from minus infinity to plus infinity.
Oh, okay.
When I make it a cosine series, I go from really n equal 1 to infinity, and the cosine gets that factor of 2 in it. That's the reason for it. Yeah.
If we do that for the transfer function, why don't we do that for the middle stage current that we have?
The what?
So when we sign for I of t, we say from n equals 1 to infinity.
But all values are the only that count, right? Well, I'm sorry, what are you trying to get at?
Why don't we multiply that
By 2.
intermediate by 2?
Because we have the total amount of
You know what? That's my, it's 2 times C of n, that's my bad. This is the right Fourier series in the exponential form. When you come down here, there's a factor of 2, and that's my bad. I'm sorry about that. It is a factor of 2, and that would be the right answer. And you can check. Did anybody check the values of the for the values he gives for n equals 1, 3, 5? All the even are 0, but the odd. Only thing you need to do is evaluate that, and it'll come out exactly right. Okay. I hope I answered your question. Things that could change. Well, I could put a voltage source there. I could have a series circuit. I could do something like this. Same basic concept. You all follow me? All right. Anything else before I continue? Okay. Good. All right. So we're done with EMC, and now you know why I don't like saying bandwidth is about 1/2 the rise now, because it makes no sense. The whole thing does all sorts of stuff. So now we're going into microwave. I know you're most interested in taking the quiz, but please be attentive to this part. How many know what FR4 board is? Anybody? It's that green board that has a printed circuit on it, usually for routers, things like that. It's fairly cheap. It's very thin. It has a constant thickness, and it really is copper clad on both sides. They use that to mount components. They etch off the copper they don't need, and then they have basic circuitry that they put there. They'll have basic chips, all that stuff. That is very lossy. It means that the actual material that it's made of at higher frequencies, at microwave it loses a lot of energy. It'll heat up basically if you have high power there. It is not something that is very efficient for very high frequency precise work. So there's something called Duroid board, and it's a high frequency laminate. How many have heard of that? Anybody? You have? Okay, good. That's expensive. It's about $100, probably a lot more now, a square foot. It used to be $100 a square foot before COVID. Now it's probably $200-300 a square foot. But all either of these things are boards, really like this, that have copper on the front and the back, so that they're basically plated copper, and they have a uniform thickness, or called T, as such. Those boards are ideal for mounting circuit elements, and here's why. That's copper, it's conducting, right? So what happens is, when I mount all my devices, I have little points where I need to have these things connect. I want from here to here to connect, maybe from here to here, and so forth. You get the idea. I want those points connected because I'm going to mount components on those points where the actual, really, it would be a leg of, or a pin on that chip. There'll be a chip holder there, will fit right in there, okay? Now, once you know where that's going to go is, you do something where it's called lithography, where you pattern this. Normally you develop either the places you want the copper to stay or the places you want to remove the copper. There's positive and negative lithography. Then, once it's developed, or once you do that, you put a film on here and you basically expose it to usually UV light, and it'll develop the film, and then you do it's a simple solution wash off the film that was developed usually. It depends if it's negative or positive. Because you'll remove the film that you don't want, and now the film that's there covers the copper that you want left. You all hear me, class? You take that and you put it into an acid dip. It depends on, you can do it with reactive ion etch, or should say plasma etching, but then you remove all the copper that you don't want, and it won't destroy the laminate. So the FR4 or the high frequency laminate, that stays, but now you remove all the copper but the copper you want. That's the idea of this. Now the width and the thickness of these lines are microstrips, and they have a given impedance that you can design for. I'm trying to give you an idea of why we do what we do. That's what we're going to talk about in chapter 10. It's microwave engineering, but it's basically on these type of boards. All right? It's microwave engineering with a focus on applications to real-world designs. And I've used this stuff. We've built antenna circuitry on it. We've done a whole bunch of stuff. It's not hard to use, but you have to be clear that the thickness of that board and the line width that you get will determine the characteristic impedance of the lines. It's real important to match the impedances. If you're 50 ohm input impedance, you want 50 ohm lines. So he has a bunch of stuff about impedances in there. I'm going to stop there. I'm going to tell you, I'd like you to at least do the reading assignment I give you for Monday and a few of the problems. Because on Monday I'm going to start, and I'm going to go right in to the section on L-section matching. And I'll send you something with rotated Smith charts. So we're going to move kind of fast today. All right, take everything off your desk. And then, maybe I'll start on this side. When you did this, it's an anyway. Guys, not here. 2, 3, 4, 5, 6. 1, 2, 3, 6, 7, wait a second. Did you have both the same ones?
What?
Same numbers, is it A and B or AB?
We got a B.
B? What does the girl have next to you? Alright, you hold the B one, I'll give you an A one in a second. And this is A, so just give him that. Finally, just take the pile. I'll get the extras in a second for you guys. Make sure your names are please be clear in some of your work.